Let me begin with a quote. For centuries, architects have carried out shape computation by hand, using informal procedures and simplest of tools. Over the last decades, they have made increasing use of more formal procedures executed by computers, a development that raises challenging question of architectural theory and perplexing issue for those concerned with the future of architectural education, wrote William Mitchell in 1989 in a preface to the book titled Electronic Design Studio, Architectural Knowledge and Media in a Computer Era. This book, or rather proceedings of one of the first conferences on a subject, was devoted into 4 chapters: Theoretical Foundations, Electronic Media in Design Studio, Information Delivery System for Design, and Knowledge-Based Systems, or Shapegrammas. This over 3 decades old publication frames those categories of architectural design in an emerging computer era, yet, even it includes shape grammar, it did not recognize parametric design as separate domain. Today, architecture can be described in a variety of ways. We're looking at the amazing series of drawings of Makoto Maruyama, Japanese artist who creates ultimate 2D drawings and the models of analytical nature depicting flora of Japan. The majority of drawings and specification and models in architecture are CAD generated today, and describing geometric properties that can guide building construction is not unusual. Model is understood here not as representation of reality, as it is in this case, but its abstraction. To a certain extent, performance specification can describe anticipated characteristics and behavior of built form. Specification can describe properties as well as relationship between entities. Performance specification can deal with dependency, not unlike the familiar Excel spreadsheets that specify the value of each cell as a result of calculations involving other cell entities characterized by constraint propagation. Constraint propagation is a form of inference, not search, and stands here for logical relation among several variables, each taking a value in a given domain. A constraint thus restricts the possible values that variables can take. It represents some partial information about variables of interest. For instance, the circle is inside the square, relates to object without precisely specifying their coordinates. One could move square or the circle and still able to maintain the relation between those 2 objects. These descriptions do not have to be explicit. Responsive materials change their properties in reaction to the conditions around them. Using such technique as feedback, artists have created reactive sculptures and architects have made interactive environments that respond to their occupants or to other relevant and even environmental factors. Links to the variety of data can be established and subsequently serve as base to generate geometric forms using parametric design tools. Performance requirements for space can then be written, linking the description of architecture to experimental, financial, environmental, or other factors, says Picon in 1997. This is a prof from Harvard, from GSD, who focuses on theory of technology and computational design. The exploration of relationship between human beings and the natural world and subsequent implication of interactions between them has deep roots in our social and cultural understanding of society. Cities are direct reflection of their inhabitants, their architectural expression directly influence the living condition of their people. Designing involves establishing visual, systemic, or geometric relationships between parts of design. These relationships are developed by workflows that get us from concept to result by the way of rules. Perhaps without knowing it, we are working algorithmically, defining a step-by-step set of actions that follow a basic logic of input, processing, and output. Programming allows us to continue to work this way by formalizing our algorithms. While offering some powerful opportunities, the term algorithm can carry some misconceptions with it. Algorithms can generate unexpected, wild, or cool things, but they are not magic. In fact, they are pretty plain in themselves. Let us use tangible example like this origami crane. We start with a square piece of paper as input and follow a series of folding steps, which are processing actions, and result is a crane or output. Algorithm is an abstract set of steps which can be represented in a couple of ways, either textually or graphically. What are those steps? First, start with a square piece of paper, colored side up. Fold it in half and open, then fold in half the other way. Turn the paper over the white side, fold the paper in half, crease well and open then, and fold again in another direction. 4. Using the creases you have made, bring top 3 corners of the model down into the bottom corner. Flatten the model. Fold top triangular flaps into center and unfold. Fold the top model downward and crease well and unfold. And so on and so forth. Through 13 steps you conclude with reversing the fold to make head and then folding down the wings to receive the crane. Here are the same instructions represented graphically, same 13 steps. The architectural design process tends to be not only sequential but also iterative. Designers create solutions that in turn pose a new questions which are then investigated to generate more refined or entirely new solutions. Designers often use computer-aided tools to build models and help them visualize conceptual ideas. However, the vast majority of these models are still built in such a way that they are difficult to modify interactively. The problem becomes more severe when 3D models are geometrically complex. Changing one aspect of such model usually requires extensive low-level modification to many of its parts, observe Wasim Jabi. To address this problem, designers have begun using parametric software, which allows them to specify relationships among various parameters of their model. The advantage of such approach is that a designer can change only few parameters, and the remainder of the model can react and update accordingly. These derivative changes are handled by the software, but are based on associative rules set by the designer. Associative and parametric geometry, in essence, describes the logic of such design proposals rather than just the form of the proposal itself. This kind of design helps to create powerful interactive tools that allow designers to explore and to optimize a multitude of possibilities while reducing the amount of time it takes to do so. Engaging these parameters and algorithmic processes requires a fundamental paradigm shift from a process of manipulating design representations to that of encoding design intent using systematic logic. Algorithmic thinking calls for shift of focus from achieving high fidelity in a representation of the appearance of design to that of achieving high fidelity in the representation of its internal logic. The advantage of the algorithmic thinking is that it can build consistency, structure, coherence, traceability, intelligence, and to computerized 3D form. Parametric design starts with parametric variations. And those can be employed for the differentiation of the field, layer, or subsystem. To the extent to which this differentiation is rule-based and gradual rather than random, it establishes an order that might allow for orientation and navigation along its vector of transformation. Gradients, as well as more complex rule-based differentiations, allow for inference from what is visible to what is not yet visible. We are looking at Zaha Hadid and Shoemaker Opera House in Guangzhou in China, and we return to the detail of this image again. Although at any time the parametric model displays determinate shape according to the set of currently chosen values, the essential identity of the parametric design resides in a malleable object typology rather than its momentary shape. This means that the design consists in the relationship that are maintained between the various elements of the composition. In fact, design model is conceived as a network of relations and dependencies. The generation of alternative options remain viable and economical deep into the detailed design without requiring abortive modeling and drafting work. This is advantageous, at least theoretically, for the sake of continuous design adjustment as a design progress and for the sake of generation of options and variations. The parametric model can be conceived as general building plan or genotype for the generation of many different versions of phenotypes that might coexist rather than substitute each other as options. Versioning might also be applied within a single building element via the versioning of components, like generative components, according to Shoemaker. Parametrically and algorithmically built models can react to their real-life counterparts when subjected not only to the user changes of geometric parameters, but also to structural forces, material behavior, and thermal and lighting variations, as well as contextual conditions. Because they are accurately represented, the internal construction logic of structure at hand. Parametric models can also be translated into geometries and can be digitally fabricated. Well, let's start with a quote by Shoemaker, which says, "We must pursue the parametric design paradigms in all the way, penetrating into all corners of the discipline. Systematic, adaptive variation and continuous differentiation concern all architectural design tasks, from urbanism to level of tectonic detail. This implies total fluidity at all scales," says Shoemaker. His fundamental themes in parametric design include versioning, iteration, mass customization, and continuous differentiation. Having said that, you might wish to observe that his detail of his project Guangzhou at the level of assembly and fabrication fails, and it is attesting to the considerable gap between theoretical geometric model, associative model, and the actual fabrication and assembly, which exists still today in many cases. So let us define those terms mentioned by Shoemaker. Let's start with the versioning. Versioning is borrowed from software development field, and the term refers to the process of creating versions or variations on a theme, musical terms. If you will, a certain design solution is based on varying conditions. Parametric software allows a designer to create prototype solutions that rather than being cast in static CAD format, is wired almost like a string puppet would be. The wiring allows design solutions to be tweaked and manipulated, creating new versions when new forces and conditions arise. Let us now consider iteration. Iteration again is borrowed from software development field, and the term iteration refers to repeating set of steps. In the case of parametric architecture, iteration can be, in principle, can create variation at every pass through the same set of instructions. Examples may include varying the size, shape of the floor plate as one builds skyscraper, or changing the angle of modular cladding as it is tiled over an undulating surface. In addition to producing variations, iteration can be powerful a tool for optimization and for minimizing the time needed to achieve that. Using a fluid parametric system which can give immediate feedback, designer can generate solutions and test them rapidly by iterating through many possibilities, each created with a different parameter. Mass customization is one of the main successes of contemporary process of manufacturing, while the Industrial Revolution was characterized by mass production. The machines are able to produce used to be able to produce thousands of copies of same prototype. However, given the advent of digital fabrication technologies, we are now able to change the manufacturing instruction between each object. Since the process is parametric and robotic, it often costs the same to mass customize the manufactured products as it does to mass produce the same quantity of identical products. Continuous differentiation, which kind of combines the upper three factors, alludes to the future of version, iterative, and mass customized parametric work, that allows for difference to occur within continuous field of rhythm, as opposed to mere variety, parametrically varied instances within an overall group, curve or field maintain their continuity to other instances before and after them while uniquely responding to the local conditions. Let us now talk about characteristics of parametric design system. What is a parametric design system and how can it improve the design process or help explore possible design alternatives? All parametric design systems have similar constructs, namely object orientation and inheritance, and families, of course, and parameters. Let us briefly review those concepts, starting with object orientation. Modern parametric software uses an object-oriented approach in design. The user interacts with parametric system in a manner that reflects the internal algorithmic structure by creating and modifying objects such as circles, spheres, doors, or walls. A parametric system usually stores those objects in an object-oriented database. Each object then has values that determine its attributes. For example, circle will almost certainly contain an attribute called center or position and another one called radius. It will also contain an attribute called name that identifies the circle. If one wishes to reference the value of radius of a circle, named circle C, one might encounter the following term, circle C radius. Values can either be consistent, for example 100 meters, or could be functions which need to be evaluated to compute the final value. The power of functions is of course in the value placeholder of an attribute it can derive its value from values of other attributes which can belong to other objects. Consider following hypothetical function of the radius circle on the screen. C radius equal distance point A, point B. The above expression specifies that the radius of a circle is not constant number but is derived from distance between 2 points, and in such case we can call the variable C a dependent variable that depends on other values. We can also describe such constructs as associative. Association of parameters with one another allows us to derive unknown entities from the known ones. Now, a few words about families and inheritance. Objects that are of certain characteristics can be organized as family of class or family of objects. Class or family of doors can contain many individual members: hinge doors, sliding doors, folding doors, etc. The advantage of grouping several objects into family is that they can share certain attributes with their siblings and inherit attributes from parents. It is much more efficient to organize shared attributes only once in a parent object than to have to customize all the attributes and values for each offspring. For example, the system can simply tell the circle to draw itself, or it can ask a door to reverse its swing. At the heart of the modern parametric system is term parameter. The word parameter derives from Greek for para, besides or instead of, and metron, measure. The word parameter is often confused with variable. In parametric CAD software, the term parameter usually signifies a variable term in equations that determines other values. A parameter, as opposed to a constant, is characterized by having a range of possible values. One of the most seductive powers of this type of system is the ability to explore many possible design variations by modifying the value of few controlling parameters. We are looking at a drawing produced on parametric software CATIA, which was used for design, production and assembly of Boeing Dreamliner. The parts of airplane were produced in a geographically distributed factories across North America and assembled in Seattle. This was possible without any test to put it together, and first complete airplane produced totally with parametric software. CATIA, by the way, is a software also used by some architects in US, among them Gary Technologies. I would like now to read the discussion of taxonomy of parameters by Wasim Jabi. This is a very telling text, so let me begin. Parametric design is a process based on algorithmic thinking that enables the expression of parameters and rules that together encode and clarify relationship between design intent and design response. It is only natural that computer-based parametric systems focus mainly on geometry and typology. As any other system, parametric design system is defined by its input, algorithm and output. Today, we, with geometric algorithm, can invent very complex geometries. The real challenge in parametric design is not how clever the algorithm is, but how complicated the output is. Or how complicated output is, but in a selection of initial input parameters. What parameters exist beyond geometric one? In order to truly connect design to the everyday activities, we need to understand and represent some issues that designers work with. Apart from geometry and typology and topology, we need also parameters for architectural components, materials, environment, etc. Below is an attempt to classify those parameters in hope to address deficiency in the current generation of parametric system. Those definitions, as I said, by Wasim Jabi. First, mathematical parameters. Mathematical parameters are the most basic type of parameter that are already understood by 3D modeling software. For example, numbers, logical values, or even strings of characters which represented internally by numbers. Many parametric systems, such as spreadsheets, that are powerful parametric system in their own right, only need this level of parametric input in order to calculate very useful outputs. Second is geometric parameters. Those are high-level entities that are built out of lower-level mathematical parameters. Examples include points, lines, surfaces, and solids. Most current 3D modeling software can represent and parametrically modify geometric constructs of various types. 3 is topological parameters. Those describe how two or more entities relate to each other. They could be connected to above, below, near to, looking at, within, or is outside, etc. Most modern parametric systems, like Excel, are precisely most modern parametric systems excel at precisely those types of parameters. I didn't mean to say excel. We're looking at a diagram of CCTV by OMA in Beijing from 2008, where topological parameters were deployed. This is an example of diagrid pattern, which is topology that derives surface in a consistent manner regardless of exact geometry of the parent surface or resulting pattern. This allows us to use to disassociate topology from geometry while maintaining consistency of our design intents. Topological parameters allows us to consider issues of form, composition and fabrication. Fourth taxonomy aspect is representational parameters. They describe an abstract entities outside themselves. In BIM, for example, a distinction is made between isolated geometric constructs, such as cuboid and a brick wall, between cuboid and a brick wall, which allows how many bricks it has, its own weight, structural strength, cost, etc. Representational parameters allows us to describe some physical properties of what we are modeling. They also allow us to aggregate the information so we can report overall values and quantities. Now about material parameters built on mathematical, geometric, topological and representational parameters by adding and connecting several physical attributes like weight, tension, friction, elasticity and structural strength, or even U value, refraction, etc. This class of parameter begins to remove us from realm of self-referential geometric games into physical world of materiality. Here is what Professor Jabi says. Future systems for parametric design and architecture could encode materiality and physical parameters, as this will allow us to model, predict, and thus parametrically explore the performative aspects of our design proposals before they are actually physically built. Environmental parameters include frequently invisible forces that surround us: time, wind, thermal variation, movement of light, magnetic fields, Wi-Fi signals, etc. Not many of us can easily imagine the path of shadow as it travels during the day. This is why we find time-lapse photography so fascinating. Interactive facade that responds to environmental conditions, usually the path of sun, are a good example for that deployment of environmental parameter. Now the human parameters, according to Wasim Jabi, the seventh and most challenging class of parameter follows. Architecture purpose is, after all, a shelter for human from elements. While we share many physical attributes and needs, we also differ in profound ways, both ergonomically and psychologically. If we are to create humane architecture, and one that creates truly customizable spaces, we need to be able to model our clients, their intents and desires, and to incorporate that information as parameter in our design systems. We need to learn from fields of ergonomics, and especially the advanced system that aircraft, medical equipment manufacturers use to model human beings. As a good development in our field is the increasing incorporation of simulated crowd systems in case of facility planning. As the computational capability of our system grows, so will ultimately sophistications of those simulations. Incorporating all 7 classes in a parametric design system is not only tall order, but not always advisable given design situations. Knowing how to abstract the situation and build conceptual model in which extraneous parameters are excluded, but essential ones are included is part of our irreplaceable skill as designers. Parametric modeling lets you capture that conceptual model and make it explicit. This shifts the conversation according to Wasim Jabi. The challenge is not one we can shy away from if we aim to be precise about our design intent, and perhaps more importantly, strive to understand the consequences of our decisions before we actually build them. Parametric systems are only a small step in this endeavor. To be a good designer, it is always necessary to become an expert in crafting of different media. Today, those crafts are mostly digital. Craft is always learned by doing and polished by practice, but those acts are not sufficient. Designers must know the concept that underlie the forms of media they use. Designers must know the concept that underlie the forms of media they use. In today's digital media, it is primarily symbols, algorithms, and programs that form language through which we come to know what we are doing. Contemporary computer-aided design and visualization system make renderings easy. Let's look for depths, for places and forms in which parametric idea meets design situation. Let parametric models tell you the most they can. To do this, you have to enter a cycle of design in which you make, look, reflect, change, and make some more. So in conclusion, I want to reiterate that parametric design is a process based not on fixed metric quantities but on consistent relationship between objects, allowing changes in a single element to propagate corresponding changes throughout the system. Algorithmic design process in turn have opened the way to scripting and to other procedures that allow complex forms to be grown from simple iterative method while preserving specified qualities. If the parametrics technique for holistic control and manipulation of design object at all scales from part to whole, the algorithmic is method of generation producing complex forms and structures based on simple components rule. This is from Michael Meredith text titled From Control to Design, published in 2008. Parametric and algorithmic design are reshaping architecture today. If the first generation of digital modeling programs allowed designers to conceive new forms and processes, a new breed of digital techniques allow to control and realize and finally build those forms. As a form of appendix and conclusions, I want to share with you few projects and events generated by my colleagues, my students, and my participation frequently, where some aspects of using parametrics and design process were deployed. Let me start with this timeline. On the left is the start of the project, on the right end of the project. This is a process of communication or exchange of files and images and designs, some of them parametric, in a process of development, Museum of Archaeology for Korea. Distributed participation of competition designers is, I think, significant, and as well as collaboration on networks. Some of the colleagues were located in Warsaw, some in Tokyo, some in Vancouver, some in Sapporo, and some even as far away as Krakow. This process of parametric design and a layer over networking condition of contemporary practice, I think, has some significance. This is this is the final version of the project, final panels depicting the project, but more significant here was the process. I will not dwell very long on those examples. Here are a few examples from academia, from University of British Columbia. Exercise given to the architecture students in the form of generic MEL script. This is Maya scripting procedure. And each student was modifying a script to design panel for the sunscreen. Those were perforation, which was largely constrained random generator deployment, and later geometry was fabricated on CNC and installed, as you see in the right hand side window of my office. This exercise was next year modified and used in 3D using conal sections, and this time the scripting was in I think with Rhino script. You see here again fabrication of this of those screens with CNC and their assemblies, resulting in a complex library of possibilities. Now, apart from geometry itself, attempt was made in the work of one of my graduate student, Ms. Ayel Kabe, to introduce environmental conditions to the parametric design. Slider controls on the left and two-way parametric network or matrix rather, then is translated into environmental raw data and translated into the graph, and this in turn in form of the array is generated as a three-dimensional screen responsive to the condition of design. We utilize this procedure in competition for Cultural Center in Beirut, and again it was used in a more complex wall system by Ayao Kabe and Tsukasa Takenaka. You see it from inside as well, the view of it, and this was wall roof system, which involved collection of water, penetration of light, and even way of planting and vegetation. This was kind of creating a surface which was responding to environmental controls. I will not go into detail into this project, but you see the complexities and opportunities emerging in the process. We utilized some version of it in our unsuccessful competition entry for Museum of Modern Arts in Warsaw. And this interest in mapping of environmental conditions was again used in this project, where landscape mapping was translated into the pattern to generate environmental graphs, and finally procedure to generate sort of analytical map of vegetation and proposed vegetation over the landscape, with condition of a roof in between roof, I guess. They done project in Tokyo later, where in Omotesando, part of Tokyo, where environmental graphs were created from the pattern of trees or even shadows, and conditions to create algorithmically generated structure, I guess, is I think depicted in those few slides. And they called it environmental graph. And one of the last projects, this one is our entry for Polish Pavilion in Milan Expo, where we utilized roof structure, which was to allude to the field of rye before the harvest. It was kinetic, I guess, system or installation. This was designed by a group of us. I mean, this was algorithmic part, which was the deployment of grasshopper, was done by Jacek Markusiewicz. Here we had a system of controls for the fans, which in turn modified the kinetics of the dynamics of the ceiling, creating user responsive, as every user could influence geometry of the ceiling through the iPhone, resulting patterns of the pavilion. So, concluding this first talk, I would like you to stay with this image. This is installation or sculpture by Alexander Calder, the famous American modernist and sculptor, who designed series of kinetic sculptures. Some of them survived and could be seen in great museums. This is what he wrote about it. Or to the most people who look at the mobile, it is no more than a series of flat objects that move. To a few, though, it may be a poetry.